All right, so starting with numbers 18, 22, and 24. Let me give you a second. 18, the answer should just be 1, using a table, I think, right? Number 22 is a DNE, but they show you how it was DNE. From the left or from the west, it was approaching 0. Sorry, it was approaching 2, but from the right, it was approaching 0. Number 24, also DNE, and it shows why, as far as what you should have gotten as you approached one side or the other. I don't know why there's a random yellow box down there. Not exactly sure. There's a lot going on in this one. Let me see if I can full screen it to show you guys the whole problem. Ooh, A through H. Can I zoom out? Got a little small, but you can see it all. I'll give you a second. Should be getting pretty close. Which one? A is DNE, B is DNE, C is 4, D is DNE, E is DNE, F is 1/2, G is 2, and H is DNE. AJ. Let me check out the question itself while I have you guys finish grading. What number was that? 20, 26. Positive infinity is the best answer. They were answering their technical description. But why would letter B, because you guys should have the graph written down, why would letter B still be DNE? If letter H should be positive infinity, why would letter B still be DNE? There's no 2 lines approaching. I don't disagree with what I think you mean. Who can say it a little bit more concisely? Yeah, they don't agree. They're approaching different infinities. So since the one-sided limits don't agree for letter B, that's a true DNE. But for letter H, as x approaches 4, good AJ, that should be positive infinity. Is number 68 our last even? Okay. Do you guys have any questions on the evens that you just graded besides the one that AJ just asked with H? Or odds from last night? Sorry, over the weekend. Yeah, Grace. Okay, because they were giving you clues, right? Now, here's the dealio. This is only one example. So you could write this one down and be like, hey, this one fits, and then trying to compare to yours to see if yours fits. But let's go ahead and check out. Let me get out of full screen real quick so I can access what I need to. But this is one of those times, and it happens every now and then because the book likes to give questions that make you think kind of creatively and outside the box, which is good. Just gets a little tricky sometimes. But this is one of those, as soon as you see answers will vary, you have to think about yours and be like, does mine fit the qualifications that they asked? So what were the things that had to be true? Now, when they were saying these first two clues, are those approaches or are those ats in the sense of what they're talking about? What would you guys say? Yeah, they're at, so they're actual values. So at -2 and at +2, we knew from those first two that we had to have points at 0. Now, as soon as this went to the limit as x approaches -2, x is 0. That means from either side, whatever the graph is doing, from either side, they need to be approaching 0. Now, you could have done like something like a simple line just going through, because from either side would have approached 0. You could have done any sort of like parabola, any sort of cubic function. You could do any basic function. You can have a sine function if you want. You just need something that crossed through that point smoothly. Can you guys give me an example besides like this weird absolute value-y thing that happened? What did you guys have going smoothly through that point? Anybody? Yeah. Okay, cool. So you can have a parabola going smoothly through that point. Now, at some point, if it was a parabola, could Christina keep going with the parabola and have it hit that point? No. So at some point, she had to switch to a piecewise function and say, uh-oh, I needed this thing to somehow connect to that thing. Now, real quick, can you guys look at the directions in the problem? Did it say anything about the function being continuous? No? Okay. So then, at this point, Christina, did you have it connect to that one at all? Yeah. Like a line? Good. So you could have it go just straight down. Be like, well, I need to connect to that point. Is however she connected, she could have done like a cubic-y thing and had it be like, whoop, whoop. However she connected to this point, whether it was nice and smooth or whether it was jagged, once she got to this point, or once, what do you have to do in order to make the limit not exist? Make some sort of other location and break it. So whether you went down here and did some sort of linear function, whether you went up here and did some sort of parabola, what they did is they went whatever function, I think they did like a weird line, then like a radical function, and they were like, oh no, I need to go down, break it, okay, go down. So it wasn't so much important that you had like a line and then you had like a concave down thingamabob, then that you had that. The important part was, did both sides, as you came into this point, did both sides hit there, meet there? And then on this one, was there at least one side that came here and the other side went somewhere else? Did you at least have one side coming to the point and the other side going somewhere else? As long as you had those two things true, you would have had all of that. Well, 3 things. The 2 points going through from either direction and then somehow being broken. You're fine. Is that cool? Was that hard for anyone else, the whole like make up your own graph giving these clues? Okay. And you're going to see more of them. But do you see how you get to be creative in the sense of if they don't tell you anything else, you can use parabolas, you can use lines, you can use cubic functions. You just have to make sure smoothly going in, broken. Does that kind of make sense? All right. Were there any questions that we had besides number 30? Whether odds that you graded last night got stuck on or evens, AJ? 27? Oh, that's not what I wanted, Santo. Okay, what were the directions that you got stuck on?
This is
Like a piecewise f of x equals with a big old brace?
Yeah.
Cool. Yeah. Okay.
x squared, x is less than or equal to 2, minus x less than 4, 4, comma, x greater than or equal to 4.
Okay, so you have 3 pieces, yeah? Are they asking you to kind of... Okay, what's the first thing that I ask you then? I'm going to go through and just quickly explain this one because we haven't really graphed many piecewises this year yet. We do know what x squared looks like in that we know that it hits the origin, just normal x squared. And this says do x squared for everything less than or equal to 2. So what I kind of figure out first is where my different x values are. because I'm going to go from negative infinity to 2. Think a number line. If I was just thinking number line. I'm going to do one thing all the way up to and including 2. I'm going to do another thing between 2 and 4, then another thing from 4 to infinity. That's just kind of looking at the inequalities. So I'm like, oh, parabola, no big deal. I'm going to go ahead and 0, 0, 1, 1, 2, 4. And then I stop my parabola. Does that make sense? Then I have to go ahead and say, all right, now some of you are really used to y equals mx plus b and saying, okay, go to the intercept of 8, down 2 over 1, down 2 over 1. But the problem is if I'm doing that, I'm starting at 0. I need to start at 2. I think the easiest way to do this is just to plug in and say, well, what's going on at 2? Well, what's 8 minus 2 times 2? 4. So at 2, I'm at 4. Oh, wait, that's where this guy is. Well, that's nice. Where am I at 3? 8 minus 2 is 6. Sorry, 8 minus 2 times 3 is 8 minus 6, which is 2. So at 3, I need to be here. At 4, it's going to be 0. So then I know that I'm supposed to be going down. Now, hold on. Why is that a mistake? It's not supposed to be a point at 4, right? It's supposed to be a hole. So now I would need to go ahead and come steal this guy, make it a hole instead. Because I am supposed to be going towards him, but I'm just not allowed to hit there. And then all of a sudden, for x greater than or equal to 4, well, 4, 4, 5, 4, 6, 7, 4, for all the x's, it's going to be at 4. So I come up here and say, oh. So in each of these different cases, first of all, I have the y equals x squared all the way up until 2. Then I have, for this next part, I have the 8 minus 2x as the next piece. And then for the last one, I have the y equals 4. And then once you have that, then they're like, sweet, now you have the graph. I'm assuming that they want you to use it for, say, finding different limits as x approaches, I don't know, 0 or 2 or 4 or some other points as well. But is graphing it makes sense? Cool. Is there anything else we can help with? Evens or odds going once? Evens or odds going twice? Sold. All right, cool, kids. Let's get notes open and ready to go. Busy yet? So this was the bell work that we did a little bit earlier, so then Joyce, you can come back and peek at it and make sure that it makes sense. They drew the graph and then they went through and thought on their own as to what each of the different limits would be, and then they checked it in their groups and we collaborated. And that brings us up to, let's do that another day, it's chapel day. So we're running a little bit short on time. A section that you guys will like, especially after, hopefully you'll like, especially after the summer review packet, because all last section was using tables and graphs, which is good, which is important, and which is really, really easy to mess up. But you remembered from the summer review packet, hopefully, and from last year, that there are other ways of finding limits. And it has to do something with plug it in, plug it in. So that's what we get to play with in section 1.3. Today and tomorrow, and maybe Wednesday as well, because we have a lot of examples to see. And some practice, like multiple choice questions with section 1.2 and 1.3 to do. So the nice thing is, if for any reason you got behind on homework over the weekend, you do have a little bit of grace in order to catch up, besides the fact that you'll lose some points before this next one. For each of the examples, do what you know to do. Or do what you think is best, might be a better way of saying it. Bless you, bless you. Do what you know how to do, or do what you think you should do. Hopefully they're one and the same. So for instance, on letter A, which is technically because of the property up above, but maybe you would also figure it out just from our summer review packet and how if you can plug in for a limit, you do. What do you think the answer would be for letter A? Yeah, because you can't plug the 2 in anywhere. It is what it is. And what it is 3. But that technically also follows the property right here of the limit as x approaches any constant of another constant. Maybe they're the same, maybe they're different. But of another function that's a constant will always be that constant. Which is kind of like what we saw. Oh, I think I took it away though. Which is kind of like what we saw. Me look at number 27. How for part of that graph, y was equal to 4. So the height's always 4 for all those x values. So the limit would always be 4 for all those x values in that given range. I think it was x, what, greater than or equal to 4, something like that. But yeah, the limit just is what it is. But how about letter B? What changes as soon as you have an x variable in there? Plug it in, so the final answer just would be -4. Which is technically what this property says. Not that we need to memorize it, though, because plugging in C gets C. It's more of just understanding the idea, which is why for this one also, x to the n, or for x squared in this example, it's as easy as just plugging in and saying 2 squared is equal to 4. So this is kind of just forming the foundation. And we could keep on going and memorize every single type of different function that you'll see in the limit and how it works when you plug it in, or just say plug it in. So yes, there are properties. Yes, they're good. The only one that I think you guys really need to focus on in the sense of be prepared for, and sometimes it gets tricky, is probably just the first one. That's the one that gets a little tricky, and if you want, you could go ahead and highlight A and say, okay, yeah, that's right. Whenever I have limit of a constant, it's itself. Just a few people tend to get kind of confused and try to do something with the 2, and then it gets all weird and wonky and wrong. But that's just the one that's probably just the most confusing out of all of them. But then you have this page, which is helpful in a few different ways. Because this lets us think about different types of functions that can occur. So not just thinking about basic ones like x or x squared, x cubed, x to the 4th, but what if now we have like an addition or subtraction of different terms, or multiplication of 2 different functions, or division, or whole functions, powers? What can we do? And this is basically telling us that we can deal with them 2 different ways. In the sense of we can deal with the f and then the g and then put them together in the proper way. Now there are some pretty easy applications to this. But there are some tricks that kind of come along. So we're not going to make this a forever card also, but I still want you to get in your notes because there are a few times this gets a little weird. And it's helpful to have the properties to come back and look at and be like, okay, wait a minute, was that legal? Yes, we have that whole idea of plug it in, as long as it works, we're good to go. But on the AP, sometimes they love to give you just enough information. And very commonly you think that they didn't give you enough. They gave you just enough, but it's really easy in the way they give it to you to think that it's not enough. And these properties are some of the things that let us keep going even when it seems like they haven't given us as much as they should have. Sadly, there are no impossible problems that they will give you. Sadly, no impossible problems that they'll give you. And quite a few of you probably, if you've gotten down this far, are seeing the example and you're like, psh, that's easy, I know how to do it. And that's great. But the reason it's legal for you to do what I've taught you, or at least I've tried to last year and then in the summer review packet, I exposed you to again. It's because of the properties right above. So the properties say either you can find L and you can find K, because they give you actual little function pieces, and you can find these limits and then use them properly. or they cannot give you the functions at all. They can totally keep the functions hidden, but give you the L's and the K's, and then you should know what to do with them, just by nature of the properties. The one that we have to watch out for, in the sense of not just being super straightforward, although it should be as long as you know domain, is that we do have to be careful of that denominator. And the rest of them we have to be careful of, like domains and whatnot, but usually that should stick out pretty clearly. The hard thing about the quotient is that you're taking two separate functions that weren't being divided and then putting them together in a division. So then you just have to keep an eye out for that denominator, just in case. Just in case. So who has the final answer of the limit being 18? A couple more seconds. AJ, go ahead, because they're still writing. Oh, you were giving me the answer. Sorry. I thought you had a question. I was like, ooh, good, we'll do a question. Yeah, it is going to be 18. But the reason why it's going to be 18 is because technically up here in the limits, which I don't make you write every time, you should be thankful for that, we are allowed to, because of these properties, take the limit as x approaches 2 of x squared plus 5 times the limit as x approaches 2 of x plus the limit as x approaches 2 of 4. That's what the properties allow us to do. And then, like we saw on the page before, whenever we have x to the n, we can just plug in. So 2 squared is going to be 4. According to this property, we can just pull the constant out and take the limit of the inside, which we saw on the page before is the same thing as plugging in 2. And then as we saw on the page before, the limit of any constant is itself. Now, ultimately, I just say plug it in. As long as it works, you're good. Plug in the 2, plug in the 2. There's nothing to plug in. Put it all together, and we're done. But technically, the reason why it's okay is based on, first of all, the continuity of squared and x and 4. There are no discontinuities when plugging in or around or at 2, which allows us then to go ahead and use those properties legally. But from here on out, do I want you necessarily to write all this? No. That's just the reason why it's true. Janelle?
Do you want us writing the limit as x approaches 2 or 4 plus 10 plus 4?
Good question. No. And here's why. Let me put the equals. We only have to keep rewriting the limit until a, or the constant x, has been plugged in. As soon as the number has been plugged in, the limit is now, we could say the limit is being accomplished or is being solved or has been applied. That's a better way of putting it. So the limit has been applied, and now we're just finishing it off. Does that make sense? Okay. But if we were to ever, like 0 over 0, keep going, need to come back, then the limit is still in there. We haven't actually been able to deal with it yet, so that's why we keep rewriting it. Good question. And another quick, when you guys were reviewing, or I should say correcting your summer review quizzes, I think I made a point. I don't know if I took off points every time. I think I was kind of generous on this one. But if you wrote the limit next to the 18, that's technically incorrect. So the limit shouldn't be rewritten in either of these two steps, including the answer. If you want to write what equals 18, you'd have to write the whole thing, not just limit. It's like saying, oh, square root is equal to 2. Like, what? Oh, okay. You can't just write limit. He's just like an operation in a sense. You need the limit of x squared plus 5x plus 4. Okay, you can't see the top. So in the last 2 pages, all we talked about were polynomials. Now, you don't necessarily need to write this whole thing down. Let me show you what you do need to write. Last year, I think we talked about how for well-behaved functions, you just plug in. And so this is just a listing of well-behaved functions. So the first thing that we always try when finding the limit, because of all those properties, is try direct substitution. Try to plug it in. And if, I think I moved him for some reason, I'm sorry. And if it works to plug in c to f of x, f of c, which many times it will work, I just don't like the many times there, that's awkward. Try direct substitution, and if f of c exists, then f of c equals the limit, and we're done. And so you don't necessarily need to write in all these unless it helps your brain to be like, okay, cool, I plug in when it's under a radical. Okay, cool, I plug in when it's a fraction. Okay, cool, I plug in when it's a composition. Let me highlight the ones that might be trickier. Like the denominators, the composite function might get a little tricky. And the trigonometric ones. So on these ones, we might watch out for domain just a little bit. But for the rest of them, polynomials are always well behaved. Rationals are always well behaved as long as q of c is not equal to 0. But we already talked about that one on the page before. Watch out for the denominator. Radicals always well behaved as long as it exists and isn't imaginary. If it's imaginary, we're in trouble. We'll just say DNE. But they shouldn't give you one that's going to imaginary numbers. Composite functions, you could just plug in the inside, deal with the limit, and then come to the outside. Once again, only if the domain works. If it's DNE, well then we'll just go ahead and say DNE. Unless it's a 0 over 0, but that's coming back up here to the rational functions. Trigonometric, remember tangent. What else? Cosecant, secant, cotangent all have vertical asymptotes, so we'd have to watch out for those. But besides the vertical asymptotes, we're good. Just plug in. Then at the very bottom, it says plugging in thing. It works for other stuff like a to the x or e to the x or ln of x or log base whatever of x. So who's well behaved? All of these guys are. Unless you have to deal with a denominator or imaginary numbers or vertical asymptotes. And as some of you guys have already realized, or unless they try to piece these guys together, because they don't always go together nicely. And if they don't go together nicely, then sometimes we'll have limits not exist. That's kind of your basic graphs in some way, shape, or form, because your basic graphs have what? Y equals x, and y equals x squared, and x cubed, and square root of x, and cube root of x, and sine, cosine, tangent, secant, cosecant, cotangent. I should have said cosecant, secant, cotangent. And e to the x, and ln of x, and 1 over x, and 1 over x squared. All of those fit into one of these categories. So if it helps your little brain, not that your brain is little, sorry, that came out, I don't know why that came out weird. Lo siento, did not mean to be offensive. Plug in. Whenever possible, plug in. It's a Monday. I got stuck in traffic this morning. It's just one of those days. It's okay. We'll blame CSUN. They were starting today. I don't know if that was it, but do you guys notice more traffic today? Oh, just a few of you. All right. So, what do we do if we have something crazy like this? Limit as x approaches e of e to the x minus 2 over 3. We haven't seen any properties where we memorize what to do with e to the x. But wait, what did the last page say to do? Plug it in. It says on the bottom for transcendental functions, but we'll just try to plug it in. And guys, is there any problem if we plug in e to the e minus 2 all over 3? It's gross. Can anybody say it's gross? It's gross. It's disgusting. What is that number? I don't know. 2.71828 to the 2.71828. But is it right? Yes. Is it fine? Yes. Why? It exists. It's a number. I could do that in my calculator and I could get a decimal. Not going to. Life's too short. It's gross, but it's right. Does that make sense? Okay. So then what if we had something like this happening? The nice thing is with our summer review packet, once again, none of this is brand new, right? Which is why, instead of last year where we took like one page for each of the strategies and then talked about examples of each type, not that we couldn't do that, but I just said, hey, quick reminder. Basically taking notes from our summer review packet limits. Quick reminder. if we have a rational function and if we plug in, mistakes, not mistakes, problems can arise. And one of those problems, one of the big problems is 0 over 0. I want you guys to make sure that you have that indeterminate form written down, because I'm going to use that term quite a bit. Indeterminate form. I'm going to use that term quite a bit. I mean, off and on, but it's going to come up, and I want you to tie that together with 0 over 0. But what else do I want you to tie together to 0 over 0? Keep going. Because even though that means 0 over 0, the function doesn't exist. You can abbreviate it KG, right? Even 0 over 0 means the function doesn't exist there. There's a discontinuity. It just means there's a hole. And as we've seen, hopefully, in all the graphs that we did in section 1.1, 1.2, just kidding, even though there's a hole, there can still be a limit. So we have to remember things like dividing out by factoring, synthetic or long division, rationalizing, multiplying by the conjugate, or simplifying complex fractions. With that, kiddos, you are totally ready to start tackling this homework, because the summer review packet you already got practice in. It's chapel day. Get out of here. I'm sorry, we're 20 seconds. But as you can see, this section is going to feel familiar. But some of you guys did not ace the part of the quiz and got a little lost in limits part of the summer review, which is why we need to practice it now. Happy Monday. I'll see you guys later. See you in chapel. If you didn't turn in your corrections, zoop, zoop, zoop. Get it to me before you